So when people want to start with EMC simulation, I have the feeling that it's sometimes really difficult to get an idea how EMC simulation works, what methods out there, and how to model a complex product in terms of EMC performance. And this is why I would like to give you an introduction and share some ideas with you how to approach this really complex task of building a EMC simulation model. And how I would like to start is actually by using the terminology we know from EMC without simulation itself. And in EMC, you typically characterize an interaction by defining a source, a coupling path, and a victim. And what I will do today during the presentation, I would show you how each of these parts, source, coupling path, victim, can be modeled and how we approach this modeling. And I hope that this will give you an idea how to build a simulation model and why certain things are done the way that we are proposing. So let's start, of course, with the source. I have picked an inverter as an example here. So inverter, switching the current from example, from a battery to a motor. And an inverter is, of course, due to the switching, generating some noise. And when we would like to start model the inverter as a source, we start actually with the functional schematic, right? So this is the functional schematic. We have the battery on the left-hand side, a DC link, then the H bridge, and a motor, right? And when we apply a PWM signal, in this case, it's a 10 kilohertz PWM signal, we see that we can generate the sinusoidal signal here with a frequency of 500 hertz. So this is the way we would model our inverter in terms of functional properties. But how can we take such a source model basically and extend it towards a EMC simulation? So first of all, we of course need to add the victim, as you can see on the top right side. And the victim in a conducted emission measurement, I'm assuming a conducted emission measurement here for the inverter. The victim, of course, is the LISN, the line impedance stabilization network. So you can see I added the LISN over here also as a circuit schematic. And once I have the LISN, of course, I can record the simulated signal in the time domain, or in EMC, typically you would look at the spectrum in the frequency domain, right? So we have now defined the source. And the question would be, how do we get the coupling path into it? And there's a number of coupling paths, of course, in a complex product. And the first and the simplest, let's call it coupling path, are, of course, the parasitic components. So what I'm adding here, you can see I'm adding a resistance to the source simply because a source will not be able to drive infinite current. So I'm limiting the source to get a realistic source estimation. And I'm adding parasitics to the DC link capacitor because I know that the capacitor itself is not ideal. A real capacitor will have a curve like it's shown here with the red line. It's capacitive. Then we see the ESR, basically the equivalent series resistance. And above a certain frequency, the capacitor turns inductive. The same you can do for inductors. And what I added here, I didn't model the inductors in detail, but I added an additional capacitance, a common mode path of the filter, of the motor, which couples from the motor, for example, to an enclosure, right? So we are now enriching the functional schematic with some EMC specific inputs. And these are right now just the parasitic of the components. But of course, in the next step, they are not only the parasitic of the components, but they are all the parasitics of the interconnects. Basically, every piece of metal which connects your component has a certain parasitic values. And I'm trying to demonstrate this as a simple case. So we have some coupling on the power cables showed here with the 50 nanohenry coupled to the other 50 nanohenry. And we, of course, have parasitics on the PCB or on the inverter itself, on the inverter module itself, that I'm adding here on top and on the bottom. And there will be maybe some parasitic couplings of the bus bars, which I have modeled here as capacitors. So if we add all of these parasitic components, of these parasitic values, not only of the components, but also of the interconnects itself, we can build an EMC simulation model. But obviously the main question is, how can we get the values, the parasitic values of the interconnect? It's not that simple, right? The geometry might be very, very complex, and analytical equation will typically not work. Maybe nowadays people will ask ChatGPT, but good luck with this. It will not give you the values of a realistic geometry. So there is, of course, one way while we are here, it's to use a 3D simulation to extract the parasitic values of all your interconnects. So now we're taking an inverter model. So this is the same inverter that we previously have had on the schematic. Now we have the real implementation, the physical model of the inverter. You can see we have the input wires coming in here. This is the inverter section with the 6 transistors, some input filter, and then the output over 3 bus bars to the motor. A very simple model. And let's discuss what can we do with 3D simulation on it. Obviously, we can start section by section, right? Like I said before, every track, every bus bar has its parasitic values. So we can take a so-called RLC extraction approach. We take individual pieces of the whole system, like I selected the bus bars here, and we extract the RLC values for these bus bars. To do so, I basically define at each bar, I define the entry and the exit point for the current. And then the solver calculates the resistance, capacitance, and the inductance. And I can take these values, of course, manually, like as shown in this picture here. I can read these values, put them on the schematic. But that's, of course, a very manual approach. I can do it automatically by letting the solver export a SPICE model that we see here on top. And the SPICE model contains basically the circuit information about the RLC models of the bus bars. So this is an approach which is, of course, human readable. People understand RLC elements. It's a so-called partial approach because we have current sources and current sinks. So we can calculate the inductance even if the current loop is not closed. This is something which is a special property in the RLC extraction, which, for example, a full wave solver does not work this way. But that's fine if we would like to export this this kind of information and we would like to read the RLC values, but we have a number of limitations. RLC models are only valid for electrically short structures, so you cannot model resonant behavior with it. And obviously, RLC models are difficult to include radiative effects. So this is a step, I would say, in between, which we can do if we want to understand how a RLC model works. But in the following, I will move towards full wave solvers to have, let's say, a more general description of the structure. So here's just a picture, basically how the SPICE file, how the interior of such an exported SPICE file looks. So you see it generated by the partial RLC solver, and it really writes some resistance, inductance. These are some elements to the HR elements to account for resistive coupling. And then we have capacitances and coupling of the inductor. So as you would typically write a SPICE file, maybe manually. If I do it now for a system level type, what I did here, so this is now the whole inverter, not only the bus bars, I can do it. I can define 61 nodes. You see at all the positions where I later would like on to connect components, like, for example, connect my transistors, connect the capacitors. I can build such a model, but of course, with 61 nodes and couplings between these different nodes, the advantage of being able to read the values is just going away because it's far too complex to read an RLC file, a human reading an RLC file, which has 61 nodes which couple to each other. It's just becoming too complex. So the advantage of reading RLC values is somehow gone when you move towards the system level. So we have seen that the RLC extraction is a nice tool, but it got its limits simply. And how to overcome these limits? Instead of using RLC values to describe all the couplings between the interconnect, we move to S parameters, which is a black box description we can no longer simply read, but we get rid of the limitation that there is no possibility to model radiation, because with S parameters, you can also model radiative coupling. We can have also additionally a kind of unified workflow, not only for the conducted emission with partial RLC, we have a workflow which works for conducted and radiated emission. And we have the possibility also to plot, we keep the connection to the fields, which is not possible in the RLC model. I will show that in a few steps. It requires a step if we want a so-called vector fitting step, if we would like to run the simulation on the circuit. So we extract the black box model and we run a transient simulation of the circuit, basically of the inverter that you have seen in the beginning. It requires a step in between, which is called vector fitting, but that step is very well controlled, and we have capabilities inside the CSD studio to also perform this conversion from S parameters into a time domain SPICE circuit. So if we would like to simulate the inverter, we move to a full wave method, as I mentioned, and there's a number of full wave methods already in the CST studio. But for the inverter particularly, we use the finite element method in the frequency domain. So this using a tetrahedral mesh, as you can see down on the right-hand side, it works down to very low frequencies. You can basically solve at 1 Hertz. There's no problem, and extract the right resistances. At overall, the frequency domain solver scales very nice with multi-core CPUs if you would like to increase the simulation speed. So that's how the frequency domain solver is applied. With the change from the RLC nodes that we have used in the RLC extraction towards so-called ports, because if we describe a structure via S parameters, we have to use ports for this description. So you see this change. You see now, instead of this green nodes that I had before, I have this red cones, which are the ports basically. And ports work slightly different. I cannot go in all the details, but you see that instead of having 61 nodes, I moved to 29 ports, because basically for a component like a capacitor, I don't require 2 nodes. I just require 1 port. That's why this overall number of connections has been reduced. And now I have a black box, which basically describes all the coupling paths which are present in the 3D model, right? So all the coupling paths is inside this one box saved as a S parameter matrix. And now I would start connecting all the circuit elements like transistors, capacitors, what I need for the functional representation of the inverter. I would connect them to this block. And this is what we do on the next slide in terms of calculation of conducted emission. So here you can see now this is the black box now with the added circuitry. So I know that SPICE veterans, they tend to be confused by the circuitry because it looks like everything is connected to ground. But there's a good explanation, and this just comes from the fact that we are using port, and ports work slightly different on the schematic. Can't go into too many details of this, but if you contact CST support, they can give you a great explanation on how this works. And when we run the transit switch simulation on this complete schematic, we can, of course, extract all the current and voltages which are present on the circuit. Like we can see, for example, the motor current on the bottom here, the phase voltages at the gates of the transistors. But of course, for conducted emission, the most important is the listen. And the listen here is plotted in time domain, but of course you can run a FFT on the time domain. But you can also use so-called EMI receiver post-processing. Why is that? So in the measurement, when you use an EMI receiver, it's not a simple FFT, the so-called sliding window technique with different resolution bandwidths at different frequency bands. So we have a post-processing feature which allows you to run the same, basically the same kind of post-processing what an EMI receiver does, and extract the values or extract the spectrum. And of course, in the simulation, you can also add or subtract the results from each other. So what I did here, I just took the individual, the single-ended listen values, and subtracted and added them to get the differential and common mode results that you see plotted here. And once we have plotted this, of course, the final step would be to compare it to some limit lines. And in CST Studio, we also offer a post-processing step, which allows you to plot the different limit lines over the spectrum we have calculated. So summarizing the whole workflow for the conducted emission, you have seen we have a source schematic, which is basically the functional schematic. We have described the coupling paths. For conducted emission, we still have the option to choose between RLC model or the S parameters. For radiated, we will not. We will stick with the S parameters, but I'm a big fan of the S parameters and less of the RLC models. They are just more versatile than RLC model. And then we had, of course, added the victim schematic, which was the listen. And all of these 3 integrants has been added together to a system schematic, and it gives me voltages and currents at basically the probes, or at the probes, and the probes are connected to the ports itself, right? So where I define a port, I can measure a voltage. That's how it works. And I get an emission spectrum. So this is the conducted emission flow. But of course, up to now, we only speak about outputs as voltages and currents. But with the 3D field simulation, we have, of course, the huge advantage being able to visualize fields. And this is something which is very advantageous if you want to debug. You can see where your fields are happening. And what I'm showing here is basically the magnetic field at 1 kilohertz. So that's it's basically the 3-phase frequency which you see going out to the motor. So you see the 3 phases with a 120-degree phase shift outgoing on the bus bars. And it's clear that this switching pattern, I mean, this 120-degree phase shift, this 3-phase current is only generated because of the PWM signal, right? So this is our resulting field, which is not just the individual 3D results. It's the 3D results, but using an excitation which has been defined on the circuit. And how this is done is one of the key features that we think that it's very useful for EMC, because it allows you not to visualize just a field which is generated by a port, because that's what we see on the left-hand side. These are the fields generated by individual ports. So you see when port 1 is excited, we get a certain field pattern. When port 34 is excited, we get a different field pattern. But these individual field patterns, they are of course not of interest for us. What we want to see is this resulting field when the PWM signal is applied. And this works via combined results. And this is a way, so the 3D solver calculates these individual fields, then the circuit simulation with the PWM signal is applied. And after the circuit simulation with the PWM signal has finished, we know what are the individual spectra at every of these ports. And then the spectra at every of the ports are taken, and via linear superposition, they are combined. That's why it's called combined results. They are combining basically the excitation pattern. They are using the excitation pattern which has been defined on the circuit and combine the individual ports to a resulting field. And it's a very powerful technique which you cannot do with the RLC solver, which is only possible to be done with the S parameters, because every individual port has an individual port distribution. And then we can combine these individual contributions to a resulting field. And this is something which we, of course, need to heavily use for radiated emission. For conducted emission, voltages and currents are fine. For radiated emission, we need the fields. It's not sufficient to have voltages and currents. Of course, you could now complain and say, but I measure a voltage at an antenna. Yes, you measure in the end the voltage, but the standard is defined, of course, in terms of the field. And the question is, can we simulate the whole thing without the need for the antenna? The antenna is basically the shortcoming of your measurement equipment, which we don't have in the simulation. We can calculate field values in the space all around the structure. And this is what I will do in the following. If you like, you can add this antenna. I would not recommend it, but there has been some comparisons run, so you can compare the field with and without antenna. I go for a path without the antenna by using so-called field probes. So this is the setup we would like to simulate. So I have a emission example of very simple PCBs driving a 1 meter long cable. This cable has been connected with a pretty realistic connector. So down here you see the 1 meter of cable and this short PCBs connected to each other. And we would like to calculate the radiated emission up to 3 gigahertz. Okay. So the cable itself, actually, to make it a little bit more interesting, you see this very light blue structure around this twisted wire pair. It's a shielded cable that makes that thing, of course, a little bit more interesting. And if we have a shielded cable, we of course need to define the properties of the shield, right? A perfect shield is boring. A shield in reality is not perfect, and a shield in reality is typically defined by the so-called transfer impedance. And we have a way to define the transfer impedance in our cable simulation tool. And Marcel, during today's session, he will talk in detail about the cable simulation tool. I just use it at this point to define a braided shield, so basically a non-perfect shield. And this is then transferred into a so-called thin panel model. So this light blue section around the cables is a special material type which allows me to include this finite effects of the shield without the need, of course, to resolve the shield, because the dimensions of a shield are very small. So compared to 1 meter of cable length, really in 3D resolving the field properties would be a large overhead. We don't need to do it. We put the shield properties into a material model and can include this with the solver. So this is our approach. And once we have set up this 3D simulation model, of course, we need to define a source schematic. And this is similar to what we did before. Before I had the inverter, now I have actually a simpler schematic, which is a 250 megahertz differential signal driven via an IBIS models. And you can see when this IBIS models drive the block, again, this block is my black box containing all the S parameter couplings. And when I drive this block, I can see it's basically a signal integrity type of result. I can see the voltage received on this side. But for emission, of course, the voltage is not sufficient. We want to see the fields. So how do we do this? Instead of using an antenna, for example, we use such a sphere of probes. So all these green arrows, these are probes. They measure the electric field at a 3-meter distance. In this case, of course, you can define them at other distances. And every individual probe, of course, now receives a signal. And you see the signal is, again, it's a very narrow band signal because we have used our combined results on this probe. So we have calculated the spectrum generated by the digital signal and used the spectrum to calculate this the electric field generated by this signal at every position in space. And now, of course, we can do a post-processing and say in a measurement, it's typically the worst case. When you measure a DUT with a turntable and with different antenna heights, what you're doing, you are measuring the worst case at every frequency. And basically the worst case is the envelope of all this individual field probes. So you see, I have all the individual field probes here, which are depicted by these different colors. And when the envelope is calculated, I get one resulting curve, which is the emission result. So that's our approach. And let's look how this can be applied to the example that I showed in the beginning. For the simulation of radiated emission, it's more broadband. We're going up to 3 gigahertz. We change the solver. We use a time domain solver. CSD offers 2 time domain solvers, the FIT and the TLM method. I select the TLM method here. It uses a so-called octree mesh, as you can see on the right-hand side. So I have a very fine mesh at the cable where it's required to resolve the cable cross-section, and at the PCB, while in the outer section around the whole setup, I can use a more coarse mesh. So the transient solvers are typically very efficient for a broadband calculation, which we have here, and they speed up with a GPU. So adding a GPU will typically bring you like a factor of 4 to 5 compared to a CPU type simulation. So this is what we run. And coming back to the ability to visualize fields. So, you know, maybe you have heard SIMULIA slogan is reveal the world we live in. And the field plotting that I'm using here can reveal a lot of information to us. Let's look at this section. So here's the PCB in flat. This is the connector. And here's the cable. So we see inside the cable, the field is very nicely confined, but we immediately can see that there are 2 positions where there's a lot of field leakage. One is the position where the connector connects to the cable, and the second is the position where the connector connects to the PCB. Basically, all the transitions from the PCB to the connector, from the connector to the shield, they are creating some field leakage at this point. So let's look into detail. Can we do something about this field leakage? How would we approach such a problem? And the original connector that I have used has been never designed to include a shield. I have just reworked a little bit to add a shield. And if you rework something a little bit, obviously it's not of good quality. That's exactly what we see here. So this connection is basically a strain relief connection, which I use to connect the shield to it. And that's not good enough. There is a lot of field leakage in this region. So I took let's say the brute force approach. I closed the connector completely. I closed this hole. I made a 360-degree connection over here. I cannot close the bottom here because, of course, the pins have to go through there. But I have a much more tighter sealing around the transition from the connector to the cable than I had before. And if we now look at the emission, doesn't seem to help that much. Actually, at higher frequencies, somewhere here above 1.5 gig, yes, there's a lot of help from this. But at this lower frequency, at this fundamental frequency of 250 megahertz, I see some improvement, but it's just 4 dB. So improve the connector, it's not helping that much. Remember, we had 2 positions where there was an issue with the emission, where we saw some field leakage. And the second position was the transition from the connector to the reference plane. And if you look here, this has been, let's say, not that nicely designed. You see that, for example, for this differential pair, which is transitioning from the board to the connector, we have a pretty poor reference layer around it. It's open to this side, and it's causing basically all the currents to go around here, which is not a good design. So I have modified the design to be much more symmetric and allow the current also flow on this section. It's still very close to the edge, which probably not perfect, but it should be much better than this. If I apply this one, I see some improvement again, but it's also only 3 dB if I improve the ground. So what's the key in here? Obviously, we are simulating, we are calculating the worst case emission. And of course, if you just close one hole, let's say in the tank, the other hole will still leak, right? So what we need to do, we have to see how the whole thing improves when we apply the improvements to both, to the transition from PCB to the connector and to the transition from the connector to the cable. And if we do this, you can now nicely see we have over 10 dB improvement in the radiated emission by fixing both positions. Okay, so that's important, and that's a way what I would like to demonstrate to you how to work with the simulation. I'm applying fixes and I'm checking if the fixes improve this, and if they don't, I have to look further, right? So it's a little bit just trying out, and with the simulation you have the capabilities to try out many things which might be much more complex. This kind of, if you have a physical connector, just changing and sealing the physical connector manually would be a problem. I know you guys with the copper tape, you can pull it around, but that's of course not how you would like to see your final design. So with this, I can quickly check how design changes affect the emission results. And finally, we can look at the fields, right? So this on the left-hand side was the unimproved case when we saw the leakage in both transition regions. And on the right-hand side, you can see the fix on the connector side obviously improved a lot. We see almost no field leakage in this section. Well, here at the PCB bottom, the structure is still open, right? The pins, there is no shield, nothing. The pins still go through the board and the board is not put inside an enclosure. But what I would like to, what you should look at is actually this section. You can see here that with this very unsymmetric transition from the PCB to the connector, it's not only this particular position that radiates, you are getting noise basically on between the ground and the power planes in this PCB, which radiates at this section, which is completely gone after I have symmetrized this transition section. So you see that I changed this position, but the fields at this position change at the backside of the board, because the current is much guided. It can flow around the pins, while it couldn't do this before. So this is a way how to use the emission for radiated, how to use the simulation for radiated emission simulation. And I have again a kind of overview. We have the source schematic, which was our IBIS models. Now, because we want to see fields, we have to go to the S parameters and use fitted S parameters for the transient simulation. And then we use this method of combined results to calculate the radiated spectrum. So we are looking at fields and not necessarily at voltages and currents. Okay, that's the radiated emission part. Let me move to cables. This will be, of course, handled in detail by Marcel. But what I want to show you is just maybe in case you cannot attend the second presentation, what we do about cables. So here's a simple cable harness defined in the front of a vehicle. And it's important that for cable simulation, as long as we are concerned with crosstalk, as long as we are concerned with line impedance calculations and don't require fields, we don't need to use a full wave method. In the radiated emission example, of course, I require fields. I need to calculate the field at a certain distance. This is where I need to go to a full wave solver. But as long as we would like to just look at the couplings between cables, near field couplings, we can use a so-called transmission line method. So what is done is you basically cut your cable into cross-sectional pieces and assemble them on the circuit, okay? And you see an example cross-section here on the left-hand side. And with this information, we can calculate like I said, impedances, common mode, differential mode impedance, even a very complex cable harness. And this is a matter of seconds to run the simulation. It's not a full 3D simulation method. It's really this transmission line method, which can deal with cables, and not only line impedance. Of course, you can calculate crosstalk between the cables. So here's an example of a power cable coupling into a differential pair. Marcel will go into more details. And in case you want to go towards fields, we have a coupling of this transmission line method together with a full wave solver. Then we can also calculate, for example, the coupling of a field, the field coupling of a cable into an antenna. Again, Marcel will go into details. I just wanted to show it quickly in case you cannot attend his presentation. Okay, another typical example from EMI is the so-called shielding effectiveness. So what is shielding effectiveness? Basically, if you think in terms of EMC, shielding effectiveness is an analysis of the coupling path, right? You want to see you have an enclosure and you want to understand what is the coupling path from inside of the enclosure to the outside of the enclosure. And ideally, you would like to do it without a dependence on the source and on the victim. However, this is of course not possible, because if you want to measure something, you have to have a source and you have to have a measurement, right? So how this is done typically in a measurement is you have a kind of sensor inside the enclosure, and you irradiate from different angles, maybe with different polarization directions, onto the enclosure, and you measure the field inside. And why you do this? To get rid of the source dependence, right? Because if you would just use one direction and one polarization, it will give you just the shielding effectiveness information for this particular setup. But of course, you want to have it as general as possible. And this is why you sweep around, you use different angles of irradiation, you use different polarization. We can do it this way, but this would require a number of 3D simulation. But we can also do another way, and very similar to the radiated emission that we've shown you. We can basically take a sphere of field props like we had before and calculate the field. I mean, in this case, it's the electric field. You can do the same, of course, for the magnetic field. Calculate the fields at this position and run the simulation one time with and one time without the enclosure. Then, of course, your shielding effectiveness will depend on the source you have defined, right? So this is the drawback. But if you have a typical source, maybe you know your PCB is aligned in a certain way inside the enclosure, and the most critical traces on the PCB are routed in a similar way, then this is a very good approach. I would not like to talk too much in detail about shielding effectiveness. It's also a part of Richard's presentation, which comes right after mine. But I would like to mention another important thing. So shielding effectiveness is, of course, frequency dependent, and especially in the low frequency, you have the possibility of the magnetic field, low frequency, basically in a let's say in the kilohertz region or in the low kilohertz region, the magnetic field can penetrate metal. At higher frequency, basically, your field cannot penetrate. Starting at a few megahertz, the skin depth is just so short that you have no field penetration. And what matters are, of course, all the openings you are having inside the enclosure where the field can leak. But there is no direct penetration through the metal. While at low frequencies, for the magnetic field, you can have this kind of penetration, and it's a little bit tricky to model, because what you don't want to do, you don't want to resolve the skin depth, which is very small compared to the dimensions of the size. You don't want to resolve the skin depth using a mesh. So how can you do this? By using the right material model. And this brings us again back to the thin panel material. If you think back about the 3D cable that I had, and I said we have the cable shield, which was the light blue. The cable shield is modeled by a special material type. And that's exactly what I'm using also here. So this is a thin panel model. So basically what you do, the thickness of the enclosure in the CAD model is 0, but the penetration is handled by the solver. And this is very, very efficient, because you don't need to resolve the skin depth. You have just a thin sheet. That's why it's also called thin panel. And you can still accurately calculate the penetration of the magnetic field. And it's a very common and much requested simulation type from customers in the automotive industry, where they are very high currents. So high currents lead, of course, to high magnetic fields. And this magnetic fields has to be controlled inside the passenger compartment in terms of human safety, right? So you have a limit, what is the maximum magnetic field to which the human body is allowed to be exposed. And that's exactly this type of simulation. So I'm showing this here on an enclosure, but also like the underbody of a vehicle. That's a very typical simulation, which is done by our customers. So that's the shielding effectiveness. Let's move to probably the last technical part, which is the simulation of susceptibility. So in susceptibility, we have seen in the mission, it's pretty detailed way, or we need to model the source, right? The source is our DUT, while the victim is very well defined. It's a listen where we measure the signal. In a mission, it's exactly the other way around, right? Your source is very well defined because it's some equipment in your lab. It might be a BCI clamp, a irradiating eye antenna, or a ESD gun. So the source itself is very well defined, while we need to work on what the victim is. Where does the external disturbance, which is put on my DUT, where does the internal disturbance is causing some issues with the DUT? So this is exactly what I had on previous slide. The source itself, we in the CSD library, we offer a number of such models. So you will find a ESD gun, you will find a BCI clamp, also I think in the next service pack, you will find such an irradiation setup. So the source is very well defined. And we can run the simulation. So here you can see we take the ESD gun in this case, and we use the ESD gun from the component library as indicated here. This models has been already calibrated to standard. So this is the ISC standard to which the model has been calibrated. And we can run nice and beautiful simulation. I couldn't resist to show such a beautiful animation where you see the surface current in such a ESD event. It's all pretty straightforward also to be set up. We have a straightforward way how to define such a simulation. We can use the so-called true transient coupled simulation, where you really sync now the schematic at every time step and calculate true time domain fields. But there's a difficulty, and that's the one I started in the beginning. Of course, it's not so easy to understand what is the victim in such a susceptibility simulation. Because in a real test, you get a pass-fail information, your DUT fails, or maybe it's causing some malfunctions. In the simulation, what you get are fields, voltages, currents, but of course not a pass-fail information, which makes this, from my point of view, actually the most challenging things, and it requires understanding how your DUT operates. The setup of the simulation is pretty much straightforward, but still analyzing the values and understanding the values is something which I typically would not recommend for a beginner at this point. But it's possible to run this type of simulations and obtain results. The analysis is, of course, mostly up to the person who is familiar with the DUT. So that was the technical part, and I would like to give you, let's say, a few hints where to find materials, because I hope I could, enlighten you a little bit on how EMC simulation is done, but there's still a lot to learn. And of course, the best thing to learn is to have some good starting point. And you have seen the models that I have used today during the presentation, and you will find almost all the models, the radiated emission, not yet, but all the other models like this inverter, this listen, some monopole emission, you will find these models right after you have installed CSD or the BCI clamp, because in CSD you will find a so-called component library where most of these EMC related models are present. So you can click there, start the model, it's set up completely, it's ready to run. You can see, you can check how the model has been set up. Also, to bring some, let's say, most of the EMC functionality together, we have, I think in the last CSD release, introduced the so-called EMC workflow button. You see also all the post-processing functionality, the functionality to define the different field probes. They are all collected into the EMC workflow button. Also the possibility to create PWM signals, which I have used for the inverter aspect spectrum and the EMI receiver post-processing, the limit lines, they are all connected under the EMC workflow button. And you will find an EMC workflow button both in the 3D part under post-processing, and in the circuit part under post-processing, as you can see, they offer slightly different options because, for example, the PWM signal, it only makes sense to define it on the circuit and not in the 3D model. So feel free to browse through them. It's really the way to collect everything EMC related under one button. And finally, of course, we have training materials, which will include also a number of examples, real life examples that have been designed by our team, which help you to go through it. I think over 8 examples are contained in the CST Studio EMC EMI training, which you find in the Dassault System EduSpace. Which brings me actually to the summary of today. I hope I could show you that EMC simulation is pretty major and can handle complex models. It's not so simple like, I mean, I have, let's say, medium complexity with the inverter, but of course there are possibilities to bring it even to very complex models, but it requires the right modeling approach. And then you start thinking in terms of EMC as a source, coupling path, victim, it helps you a lot to sort these different things out and understanding why certain things are modeled the way we are proposing. We have a number of different solvers. So during this presentation, maybe if you have noticed, I have used the so-called partial RLC solver for RLC extraction. I have used the frequency domain solver for the power electronics inverter part. I have used the cable solver to define my shield, and I have used the transient solver for the radiated emission because each of them is more efficient. It's not that one is wrong or one is right. They are just simply more efficient for the particular problem at hand. We have a number of post-processing steps like the EMI receiver and the limit lines and the examples that I have showed you in the end. So with this brings me to the end of the presentation.